Obtain the mesh file and also the full training movie by purchasing this product. The present problem simulates the process of air conditioning in an office with several computers and simulators using ANSYS Fluent software. The air conditioning system in the current model is of floor heating and ceiling cooling. In this way, the effect of buoyancy causes free heat transfer inside the office space. Due to the lightness, the hot air moves from the floor to the ceiling, and the cold air does the opposite, thus creating a circulating flow that causes the air conditioning process. The present model is designed in 3 dimensions using Design Modeler software. The geometry of the model includes an office desk and also in which 4 computer cases and 4 simulators are located as heat sources. There are also sections as air inlets and outlets on the floor and ceiling of the office. Also, the meshing of the model has been done using ANSYS meshing software, and the mesh type is unstructured. As we are going to simulate the heat transfer phenomena in this CFD simulation, it is obvious that energy equation should be activated. In this model, due to the presence of radiant heat transfer between the surfaces inside the office, the radiation model is defined as S2S model. The material of the discrete phase has been identified as anthracite, that is somehow equal to sand and dust particles. In the Point Properties tab, we can specify all the variables about the particles, including diameter, temperature, velocity, and also mass flow rate. We should set the atmospheric pressure in the operating pressure of the operating condition section. Also, all the existing walls in this computational domain participate in the radiation phenomena. This is the highlighted wall that acts as a heat wall and has a constant heat flux that is identified in this section. In this modeling, airflow enters the office from circular sections as the velocity inlet from the office floor with a speed of 0.6125 meter per second, and also the temperature of 291.1 degree of Kelvin. The air exits through rectangular sections of the office roof with a pressure equal to the atmospheric pressure. For setting under relaxation factors, we should say that the pressure-based solver uses under relaxation of equations to control the update of computed variables at each iteration. In ANSYS Fluent, the default under relaxation parameters for all variables are set to values that are near optimal for the largest possible number of cases. These values are suitable for many problems, but for some particularly nonlinear problems, for example, some turbulent flows or high Rayleigh number, natural convection problems, it is prudent to reduce the under relaxation factors initially. It is good practice to begin calculation using the default under relaxation factors. If the residuals continue to increase after the first 4 or 5 iterations, you should reduce the under relaxation factors. Occasionally, you may make changes in the under relaxation factors and resume your calculation, only to find that the residuals begin to increase. This often results from increasing the under relaxation factors too much. A cautious approach is to save a data file before making any change to the under relaxation factors, and to give the solution algorithm a few iterations to adjust to the new parameters. Typically, an increase in the under relaxation factors bring about a slight increase in the residuals, but these increases usually disappear as the solution progresses. If the residuals jumped by a few orders of magnitudes, you should consider halting the calculation and returning to the last good data file saved.
Also, with checking this plane, we can see that the maximum velocity magnitude occurs from the inlet. Also, we can see the cases and simulators as the heat sources. The inlet temperature is equal to 291 degree of Kelvin, as we mentioned before, and as we identify it in the inlet section at the boundary condition. And also the outlet temperature reaches to more than 300 degree of Kelvin. That shows that's about 9 degree increase in a term of temperature because of the heat sources of computers, simulators, and also the heat wall. The following tables represents a summary of the defining steps of the problem and its solution as a review. Obtain the mesh file and also the full training movie by purchasing this product. To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.